I guess I'll bring the meeting to order. Hello, everyone. Welcome to the July meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. Welcome to those of you who are tuning in online, either live streaming or downloading it later. Thank you very much for taking the time to join us for the July meeting. My name's Roman. I'm the meeting chair, so we'll just kick off right away. I guess just before we get going, I'm sure the news will have made the rounds through the membership. But today's meeting is dedicated to the memory of Rolf Meier, and we'll have a talk very shortly about Rolf, who was a large part of the Ottawa Centre and a significant contributor to astronomy in Canada in general. Unfortunately, it sometimes falls onto the meeting chair to have to give unfortunate news, and we're very glad that Rolf's family was able to make it to today's meeting. I'm sure many of you have very fond memories of Rolf and the interactions you had with him over the many years. So this meeting is dedicated to his memory, and we'll just proceed from there. So this is the order of speakers for today. Slightly different. We'll have. Oh, sorry. I think I just turned it off. Oh, there we go. Sorry. So we'll have, I'm just giving the introduction, we'll have Brian McCullough and Gordon Webster speaking to Rolf. Then we'll have the usual talks from Dave Chisholm and Al Scott. And our own tech master, Kujala, will be giving a talk on the transit of Mercury. Then we'll have the break, and we'll have talks then from Konstantin, Popov, and our own Simon Hanmer. So these are the new, we've had 5 new members for the month. Thank you very much for those who joined. As I always say, I hope you find this society as rewarding as I have. It's a great group of people. So let's make them all feel welcome. All right, members in the news. The first, this is a website that I hadn't heard of, but apparently has a lot of traffic, called apartment613.ca, and this is an article by Brian Carroll. Yes. By Brian Carroll, and he mentions the Ottawa Centre of the Royal Astronomical Society of Canada. And so it's a good way for us to get exposure. Apparently, it's as I said, it's a very well-traveled, very well-visited site, and it even gives a shout-out to Kujala, and it mentions his contribution to the technical side of things, and allowing our meetings to be accessible, even to those who can't be here on the day. There we go. From CBC Radio, The Current. Unfortunately, we couldn't play the whole audio, but we have one of the guests was Rob Dick, our very own Rob Dick, and it mentions that he's the manager of the Canadian Dark Sky Preserve Program and chair of the Light Pollution Abatement Committee at the RASC. And so again, this is again a good exposure for the centre and for public education of astronomy and astronomy-related issues. Now, Rob got a very, very well-deserved praise, I think, from none other than Roberta Bondar herself. I'll read it out, although it's pretty big, I'm sure you can read it yourselves, but I'll read it out anyway. Your guests have very eloquently described some of the effects on most humans, and also the beginning, talking about the past, the history, the creative part. My view, and I have a foundation in my name, that is really about reconnecting and connecting people to nature, and it goes on from there. So, Rob, you got a very beautiful compliment from Roberta Bondar. Well done. So I guess now I'll turn it over to Gordon and to Brian for the next talk.
Good evening, everyone. It's my sad job to inform you of the passing of two members of our RASC Ottawa family, Welding Hanmer and Rolf Meier. They both passed away in recent days. Welding, a familiar face to many of us here, died on Monday, July 4th at the age of 90, just as the Juno spacecraft was approaching orbit at Jupiter. And Rolf Meier died on Sunday, June 26th at the age of 62, a month after the latest opposition of Mars. Brian McCullough will be making a presentation, or presenting a retrospective tribute to Rolf in a few minutes. But before he does, a few words about Welding. Welding Hanmer worked as a geophysicist with energy mines and resources before joining the RASC Ottawa in 2000. Almost immediately, he got involved with the construction of the SmartScope observatory out at Shirley's Bay, and he was present at our meetings and events over the past 16 years. He was well known to ask key questions. Welding always seemed happy among us, and I know Brian and Bridget particularly enjoyed his company at our annual dinners in the fall. His good-natured disposition and his wonderful manners will be missed by all of us. As we take a few moments to remember Welding's life, please join me in wishing him clear skies wherever his spirit may be. Thank you. Brian?
Advance this one, go back.
Okay.
Sorry about that.
Okay, so there's Welding. I know we just had the one other slide, and I just wanted to show that up because, I mean, that's what Welding was like, right? I mean, remember, we'd see him sitting here most often, but as Gordon said, Bridget and I really enjoyed his company at the annual dinners, so him and his wife Patricia there. All right, so. Can we bring the house lights down just a bit, please? All right. So good evening, everyone. On behalf of our president, Gordon Webster, the RASC Ottawa Council, and the entire membership of RASC Ottawa Centre, it's my task, both sad and glad, to offer a few words of tribute to a departed friend, a longtime member of our centre, and a highly respected member of the broader astronomy community, Rolf Meier. As most everyone across the Royal Astronomical Society of Canada knows already, Rolf suffered a sudden and devastating brain tumor that took his life on Sunday, the 26th of June, at the age of 62. The news of his illness, first announced earlier this year by the Meier family's close friend David Levy, came as a shock to everyone, and we're thankful to David for keeping us up to date concerning Rolf's condition. I had a chance to speak with David at the General Assembly in London at the end of May, and I know how deeply affected he was by the plight of his friend Rolf. We're also very privileged this evening to be able to present this tribute in front of Rolf's wife Linda, his son Matthew, and Matt's wife Melissa, who are sitting just up here in the front row. You've shown remarkable courage and strength over the past few months, and we hope you and the rest of your family will accept the sincere condolences we have to offer you. This tribute is a result of input from many of your and Rolf's friends, astronomy friends, and we thank you for being here with us tonight. Rolf joined the RASC Ottawa Centre in 1970 and became one of our few life members. Over the years, he served as meeting recorder, counselor, Astronotes editor, National Council representative, vice president, and finally president in 1990-1991. While this level of involvement and commitment to the well-being of the centre is certainly noteworthy on its own, Rolf left his mark in other ways that drew wider attention in the form of the prestigious Champ Medal and other accolades from the RASC. You can see Rolf here on the right with other Champ Medal recipients, David Levy, standing right next to him, Warren Morrison, and Damien LeMay on the left. He was also brought him national media coverage for his 4 visual discoveries of comets, including the first comet to be discovered from Canadian soil on April 26, 1978. That Rolf became the toast of the town throughout the Ottawa Centre and the rest of the amateur astronomical community was an achievement well earned. There's Rolf with Peter McKinnon, who's here with us as well. Rolf's dedicated and innovative efforts to sweep the skies for new comets has been well described in Looking Up, a history of the RASC written by Peter Broughton, and in a recent article for Sky and Telescope that was written by David Levy. Just as Rolf was inspired by others to begin searching for comets, his example inspired others, including Doug George, to conduct their own successful comet searches, and many others of us to simply satisfy ourselves by observing the fruits of their discoveries. Doug George said for this tribute, "I remember being at the observatory on the night of one of Rolf's discoveries. He was very focused, if not intense. He took the time to let everyone have a look and then sped off to file a report. It was an exciting night and he will be missed." Of course, there were other inspirations in Rolf's life. His marriage to Linda McRae, an accomplished variable star observer in her own right, and their son Matthew, now a successful scientist. So Rolf was born in Germany and moved to Canada with his family when he was 5 years old. And as is the story with many of us, he picked up the observing bug fairly early. But over the years, Rolf would become known for the exceptional quality of his observations and astrophotography. He was certainly no stranger to celestial events and traveled widely with his astronomy friends to observe. Jonathan Buchanan recalls heading out to grazing occultations with Rolf in Rolf's Volkswagen Beetle. More on this later. A trip they made with Ken Hewitt-White, Joan Hoskinson, and Alan Miller to view the launch of Apollo 17. I remember seeing video of that a while ago. Also a cross-Canada trip with Rolf and Ken, trips to Starfest, a trip to Winnipeg for the 1979 solar eclipse, and they were all good memories for John Buchanan. And people always remember the kind of man that Rolf was. Rob Dick remembers Rolf for his unorthodox methods, wit and dry humor. I remember a trip to Stellafane, Rob said. "We walk into a pub in the early afternoon and Rolf asks if they have any Canadian beer. They say no. So Rolf says in a slightly elevated voice for all to hear, 'Oh, I'll just have milk.'" Typical, eh? So Rolf will be remembered by, this is Rob talking, by me and others through his legacy of discoveries and renowned observing talents. He's a part of our past, which makes him part of our present, even though he's now gone. Nicely said, Rob. John Percy of Toronto wrote online, "Rolf is one of the names that I knew from when I was most active at the national level many decades ago. He was an exemplary citizen scientist, whose contributions have been significant and sustained. He will be missed but well remembered." Paul Gray, the president of Halifax Centre, wrote online as well, "I joined the RASC as a 15-year-old kid in 1987, and when I learned that folks like Rolf Meier and David Levy were part of this organization, my interest went sky high. To me, it was folks like Rolf, David, and others who were giants doing what I only dreamed was possible. Rolf was always ready to lend an ear to my ideas and thoughts on observing and to give good constructive advice and encouragement. The doors that were opened to me by pursuing my interest in astronomy through the RASC happened as a result of the influence members like Rolf had on my young mind. Rolf will be missed, but I hope many of us can share and encourage others to pursue astronomy the way that Rolf did." While Rolf certainly knew his way about the deep sky, his remarkable talent for solar system observation is what many people know him best for. Paul Commission had it right when he said this for tonight's tribute. "Rolf was a great planetary man, one of the best amateur photographers of the solar system." You can see, remember seeing some of these over the past few years? There's the International Space Station going across the face of the sun. And who could forget the stunning photo animation that he produced of Mars? Just unbelievable. During my time as meeting chair, I soon learned not to tweak Rolf's slides in any way, even regarding the smallest detail. He would review the slide deck just before the meeting got underway, and if anything had been changed or adjusted, and I mean anything, Rolf would insist that Chris Tarrant put it back to original right there on the spot. In fact, we tried this out one night when Chris mentioned this to me, and we changed the font on one of his titles. Rolf was over on the side, he looked through, let's see, he goes, "What's this? That's not the font I use, put it back." But he was always generous in the way that he shared not only the results of his observations in photography, but other things as well. A number of years ago, I offered Rolf a small amount of lunar dust for his meteorite collection, and he returned the gesture by giving me a few precious flakes of the planet Mars so that I could demonstrate it to the many people I was meeting through my astronomy teaching. I can't tell you how thrilled people are when they realize they are seeing pieces of Mars right in front of their eyes. Now, from the stories I've been hearing about Rolf, people were sometimes, thrilled by other things Rolf did. And I'd like to ask former member Chris Martin to join me on stage to tell us about one such episode relayed to him by former member Alan Miller, who now lives in the UK. It involves Rolf's famous VW Beetle. Chris?
Thank you, Brian. Thank you, Brian. Before I start too, I know a lot of people would love to have been here tonight. So first of all, I would like to mention Dave and Holly Patterson, who are also old friends of Rolf, and could not. Dave was not feeling well. By the way, when Brian mentioned Rolf being a lifer, I forgot about that because I'm a lifer. So it's been a good ride with Rolf, and here we're going to talk about a ride. Alan Miller is a former member and now lives in the UK, but an old friend who loved observing at the North Mountain Observatory 16-inch telescope. The following is in Alan's own words. Rolf and I had quite a few experiences, some of which were absolutely crazy. One in particular took place out at North Mountain Observatory where the 16-inch was housed. We were both very avid observers back then, and one cold evening in February, we thought it would be a good idea to go and use the scope. We'd be the only ones using it that night. The sky was incredibly clear, but the temperature was something like -30, if I remember correctly. Rolf decided he would drive. And as you all know, Rolf was of German origin, and because of that, there was something in his DNA that uncontrollably forced him to buy an old Volkswagen Beetle. By today's standards, they would be considered ice boxes on wheels in the Canadian winter months. They were not designed for comfort, only to get you from A to B, which they did very well. I don't know if you remember the old ad of the lunar module. It's ugly, but it gets you there, and underneath, VW. However, due to the fact that the engine was air-cooled and in the back of the vehicle, the interior lacks something we all like, especially when it is -30 Celsius outside, heat. There was none. Well, there actually was a tiny bit of heat emanating from a gas-burning device somewhere in the car, but this had all the energy of someone exhaling damp air. I was prepared, however, with layer upon layer of clothing. I stuffed myself into his car and we headed off to the scope. Now, of course, there is a wind chill on the front of the car, so I was tasked with scraping off the ice on the inside surfaces of the windshield while Rolf drove, trying to see through what was basically frosted glass. Oncoming headlights were a nightmare, but somehow, after about 30 minutes, we made it to the observatory where we could warm up inside the heated section of the building. We were not disappointed with the observing, although more time was spent warming up inside in the early hours of the morning, until it was time to leave. That was going to be rather difficult now, because a snowplow had come by, widening the road surface, and the plow would have been out in the regional road just before the driveway. Frozen snow and packed ice were piled up about 1 meter high across the exit of the parking area. Rolf looked at it and said, "We can make it through that." Right. He pointed the car at the wall of ice and floored it. Now, you gotta remember, VWs doesn't have a lot of power, so when you're flooring a VW, it sounds impressive. It's not going that fast. This is the old one, folks, remember? We picked up speed, well, sort of, and hurtled forward. To our surprise, none of the broken icy snow moved, and instead of plowing through the ridge of white stuff, we went right over the top of it. We made it. But looking back to see what Rolf had done, we could see that there was something odd about the snowbank behind us. Something shiny was on it. We got out of the car to check and observed that the entire rear bumper of the VW had been ripped off. I couldn't help but laugh. It wasn't long after that when Rolf bought a bigger car, a Dodge Dart, with a real heater. And I rode in that one. That was a warm, nice car. So thank you, Alan Miller, for sharing that. And we really appreciate it.
Thanks, Chris. I should mention that Chris offered his own reminiscences of Rolf. I was talking with mutual friends of Rolf, Dave and Holly Patterson, as he mentioned, and we mainly agreed that Rolf was quiet but liked any challenge, whether it was astronomical or otherwise. Rolf was always up for a challenge. I first joined the Ottawa Centre in 1966 and was active in meteor observations of the Perseids of 1967 at Quiet Site, the Defence Research Board site where we were allowed to set up our observing coffins. Rolf was more interested in telescopic observations, and I went to North Mountain Observatory a few times with him in his wonderful Dodge Dart. I moved away in 1981 to Saskatoon for job opportunities, and I remember Rolf coming through town once in the early 2000s with Linda and Matthew. They were coming up from visiting David and Wendy Levy, and were headed over to the GA in Winnipeg. All I can say is he looked proud to be Matthew's dad and so happy to be Linda's husband. Thank you for that, Chris. Rick Wagner had this to say. Rolf always danced to his own drummer. He had a better idea on how to search for comets, so when everybody told him it was silly, he just went out and discovered 4 comets to prove that he was right. Now everybody does it his way. Everything he did to a standard of excellence that few match or exceed. His planetary images were among the best taken from a less than ideal location. Indeed, were better than almost anybody else's in the world. The Centre picnic he and Linda hosted for many years was a social highlight of my calendar. How many of us remember these events, right? Rick continues, he said, Rolf had extremely diverse interests. Witness his old museum, or his museum of old technology. His meteorite collection, his Tesla coil, that was always great at sunset, wasn't it? The trebuchet for flinging this, that, and the other thing from here to there. And launching rockets, remember that, Matt? Yeah, do you remember exploding my son's rocket? Yeah. Anyway, Rolf derived great joy, Rick says, from repurposing materials into new and novel tools. He was a real do-it-yourselfer. He was also a great friend, always willing to give advice or help out with a project. I loved his extremely dry sense of humor, often not understood by people who didn't know him. Well, as Rick said, Rolf had a knack for cobbling things together to make something out of nothing. He was a real MacGyver. If Rolf had been the professor on Gilligan's Island, he would have had the SS Minnow refloated and running on coconut shell fuel cells in no time. We all have our memories of Rolf and of the way he intersected our lives, and as much as his astronomy family misses his presence, I'm sure no one feels his loss more than the people he loved the most, his family. Seeing the photos of him and Linda together with his parents, Rolf Sr. and Inga, on Matthew and Melissa's wedding day says more about them as a family than I have any right to comment on. Except to say that the pain of your deep loss is also felt by the people I've had the honor of speaking to over the past couple of weeks. As we come to the end of this humble tribute to that we've offered with the utmost of respect, I'd like to read something to you now, an eloquent remembrance of Rolf from Ken Hewitt White, who expressed his regrets at not being able to travel from British Columbia to be here in person. This is from Ken. I've been gone from the Ottawa scene for decades. My days in the Ottawa Centre RASC occurred when the first Trudeau was Prime Minister. Way back then, in the late 60s and early 70s, the Observers Group featured a remarkably active core of nearly 24 youth members. A key figure among them was Rolf Meier. The guys and gals I hung out with were motivated and smart, none more so than Rolf. Most of us had a crazy sense of humor, again, none more so than Rolf. His was a dry, calculated wit. I realize now that Rolf's occasionally offbeat, sometimes deliberately eccentric behavior tended to obscure just how amazingly intelligent he was. And reading over his obituary, I thought to myself, I didn't know that about Rolf. Over the years, he became an accomplished professional and a wonderful family man, above and beyond his astronomical exploits in the Ottawa Observers Group. But it's those legendary successes I remember the best. Rolf's historic comet discovery, the first in Canadian soil. The 3 other comets that followed. The road trips to Stellafane, where Rolf would proudly demonstrate whatever optical invention he'd just whipped together. And the cold winter nights at North Mountain Observatory, as before IRO and before FLO, where he often depended on Rolf's tenacity at the eyepiece of the 16-inch and the duct tape and rubber bands that kept his ancient Volkswagen running. Can I reduce my recollection of Rolf to a particular moment or event? No, there were too many of them. Rolf just seemed to be everywhere in the Observers Group. He was a complete player, the sparkling personality, the skilled scope maker, the careful photographer and meticulous observer. All that and funny too. I liked Rolf. I liked him a lot. He will be deeply and sorely missed. So thank you for that, Ken. I believe that Ken's words resonate for many of us here this evening and also for those watching by video later on. As I turn the podium over to Rolf for a final presentation of his observations of Mars from 2012, and invite you to please stand and give a round of applause and a cheer to our good friend and fellow astronomy enthusiast, Rolf Meier. So.
All right, we have a number of observations, some really nice stuff to show you. Rolf's up. Rolf has some awesome images. There you go, sir.
Okay, I can remember how to operate this. So three different, completely different things here. First of all, Mars, which was in opposition a couple of months ago, and then a couple other pictures. Let's see. Okay, so it was still pretty small at the end of last year. So this is all we got then. Probably less than 8 arc seconds or so. And then January was pretty cloudy, and then in February we were away. So the next chance was in March when Mars was in opposition. Let's see. Oh yeah, I should go back here. So you see how big these images have north at the bottom. You can see how big the north polar cap was in December, but by March it had shrunk considerably because it was now summer in the northern hemisphere. Oops. That's not what I meant to do. Yeah, there it is. So you can see how small, and there's also a little bit of haze that comes out over the polar cap. This here is Olympus Mons and a cloud over it. And here, see this image here shows Olympus Mons when it's around noon time at Olympus Mons, and by the time it's evening, you'll have all these orographic clouds. That's why you get a lot of clouds on this limb of Mars, because this is kind of evening clouds. And this is kind of morning haze, kind of like fog. You always get that. This is in April when it was still getting not too bad size-wise, but starting to get smaller.
Is that big canyon anywhere in these pictures?
Valles Marineris is right here, but it is not an albedo feature, so it doesn't actually show up as a feature in any albedo pictures. So basically what you're seeing here is just light and dark areas, and Valles Marineris is pretty much the same color as what's around it, so unfortunately it doesn't show up. You're always looking at the full phase of Mars, pretty much. So you don't get any shadows in any of the craters or valleys or mountains or anything like that.
Is that fog on the very top on April 10th?
Oh yes, thank you for pointing that out. So this is actually what's called Hellas. This is not the South Polar Cap, but it's Hellas. This is the lowest elevation feature on Mars. It's like 7 miles below the actual, or the sea level, if you like, of Mars. So this is kind of filled up with haze and probably frost. Probably water frost at that.
Tell Brian you got a great face on Mars there.
Yeah, so some people think that there's a face here. Yes. So this is my favorite. This is sort of the favorite view of Mars because there's a lot of neat features there. This little notch here is defined as
Unibrow.
that's called Sinus Meridiani. And that's the central meridian of Mars, and it was defined that way because the visual observers were able to see this very sharply defined V, and they thought, okay, let's make that 0 degrees.
see something like Dzioba the Hutt on that face.
Yeah.
It's almost like a Mars Picasso.
All right. Okay, so here is a very interesting thing. This is showing 3 monochrome images on March 20th. And what happened here was a lot of people took an image of Mars and they looked at their green and their blue image and they thought, oh, what the heck happened there? And they were throwing away this data. And I was ready to throw that away too, because there was this very high altitude cloud that was showing up, but it looked like some kind of an artifact or some effect of seeing. But the seeing was actually not too bad this night. And what it was a very high altitude cloud, which seems to appear periodically. And it may even have extended beyond what you might call limb. I mean, this was already past the time of opposition, so there was actually a little bit of a phase to it already. But this seems to have actually extended significantly high into the Martian atmosphere. And it showed up best in green and blue light. The green here is somewhat enhanced in terms of brightness. It wouldn't normally be that bright. Same with the blue. Mars is brightest in red, of course, but this cloud was brightest in that, so it was enhanced. And once again, here you can see in blue light the clouds show up. This is the cloud over Olympus Mons. Okay, and April 12th we had an aurora. Interestingly, these are our solar panels underneath, and of course it ties in the solar with the fact that the aurora is caused by the sun.
Thank you, Brian, and Gordon, and Chris for that very nice tribute to Rolf. And again, if you wish to pay your respects, Linda and Matthew and Matthew's wife are down here in the front row. You can see them during the break. Continuing on, we have Dave Chisholm and the skies for July 2016. You'll notice we have the correct month this time.
Yes, we do. Okay. Okay, here are the moon phases for the month of July. Our full moon is on July the 19th. We have the Delta Aquarids meteor shower, July 28th and 29th. If we go back to the moon phases, you'll see that's not the most ideal time to be looking at meteor showers. However, this particular meteor shower can produce up to 20 meteors per hour. It runs annually from July 12th to the 23rd of August. Peaks this year on the night of July 28th. The second quarter moon will block most of the fainter meteors this year. But if you're patient, you should be able to catch quite a few good ones. Best viewing in a dark location after midnight. And there's where they radiate from, the constellation Aquarius. Mercury will be visible in the early morning, and the rise and set times are there on the slide. Venus is not visible at all this month. Mars is visible all month. Jupiter visible all month in the first part of the evening. As you can see, by the end of the month, it's setting at 10:12. Saturn is visible all month. Uranus and Neptune, both visible all month. International Space Station, the best viewing date is July the 29th, or it rises to 63 degrees. And there's a picture of the path that it's going to be taking. And I leave you with this little cartoon, and the cartoonist happens to be with us here this evening. He's related to Chris. It's Chris's son. Thank you.
Yeah, as David was mentioning, the cartoonist, John O'Doodle, is actually Chris Tarrant's son-in-law. When his daughter Heather went to Newfoundland to study, one of the first people she met was a guy by the name of John Canning, who is a cartoonist. He teaches cartooning there and does his cartoons under the name John O'Doodle. Brian has been working very, very hard over the past 2 weeks to put together the tribute we've just seen. And to make it even more difficult, Brian don't know what he was doing. Apparently he went out observing one night in his observatory, and he forgot that the entrance is quite low, and so he didn't bend down. And apparently he wasn't having much luck seeing stars in the observatory, so when he left, he decided to do something about it and banged his head and got lots of stars. And John has done another cartoon for us. Now, John, would you like to come up? Brian, would you like to come down, please? Any of you who've been with us for a while know that Brian's always the first one to help out other people.
Come into the light, John.
Come on over to the light. And just as a little thank you to Brian, we have a framed copy. And apparently, the first cartoon had been selected without David knowing who John was. That's just coincidence, one of those lucky things. Thank you.
Thanks, Gordon. You know, that's uncanny. I don't think that. I think that is exactly what Brian looks like, and I think that's exactly how it happened.
That's exactly what I said too.
Yeah, sure. Well, you're an old Navy man, aren't you? Yeah. So you know how to hold your tongue. You know, you keep a civil tongue in that mouth of yours. Good work. All right. Moving on. Sorry, this thing doesn't seem to be working. All right. Al Scott has his 10-minute astronomy news.
We bring the house lights down? Thank you. All right, I have three quick news items for you this evening. The first, the Earth has a new pseudo-moon. Astronomers recently announced the discovery of 2016 H03, not as poetic as the moon. However, this asteroid is between 40 and 100 meters in size and behaves as Earth's quasi-satellite. It was discovered as a 24th magnitude blip on April 27th this year by the Pan-STARRS survey based in Hawaii. And it has basically an orbit which is almost exactly 1 year. And it's really orbiting the sun, but the Earth kind of tugs it around because it's very close to the Earth's orbit. So every year it goes around the Earth once effectively. But the orbit is kind of odd. And I'll show you, I think this animation should work, showing the orbit of the Earth on this newly discovered moon. There it goes. So you can see that the orbit is tilted with respect to the Earth's orbit, and this object, so this is with the frame of the Earth. You can see this object is actually orbiting the Earth as well as the sun. This is what there are a lot of objects that the Earth captures, not a lot, but this does happen frequently, and these objects are called temporarily captured objects. Typically, they only complete about 3 orbits of the Earth-Moon system before being ejected, and only about 1% of them actually ever hit the Earth. This object apparently has been around for centuries, and is somewhat stable, and should be around for centuries to come, until eventually jetting off somewhere. There you go. It's several Earth-Moon distances out. It's not close to the Earth. Let's see if we can move on. The next item, you may recall a report on the LIGO Laser Gravity Wave Observatory discovering coalescing black holes. So theory is now emerging about how this system may have occurred. A system of binary black holes was discovered through its gravity waves in large laser interferometer on Earth. And there's actually been 2 discoveries so far, and both discoveries are towards the upper end of this. They actually can tell what the mass of the black holes is from the signal that they've measured. And the ones that we've seen are up towards the larger end of black holes as we know them from what could be formed from stars. Typical star mass black holes are, a few solar masses, 10 solar masses maybe. Well, these were quite a few more solar masses. And this is kind of a timeline of what may have happened to result in the signal that we detected earlier in the year. So here we have a picture of 2 zero-age main sequence stars. Let me see here. So we have 2 stars. One is 96 solar masses and the other is 60 solar masses. These are behemoths. They're huge. Here is time going from 0 million years, 3.5 million years, 3.8 million years. Large stars evolve quickly, burn quickly, and go supernova quickly. This is the separation of the 2 objects, the distance between them in, I'm not sure what the units are there. Could be solar radii. This is the eccentricity. So you see 96 and 60 solar masses. They exchange, because they're so close, they actually exchange their envelopes. So material actually streams from the larger one onto the smaller one because the larger one is more extended. And what happens is that this becomes a hypergiant, and then it collapses into a 35 solar mass black hole roughly 3.8 million years after it's born. This one continues as a main sequence star, 84 solar masses. They then have a common envelope. This one starts orbiting inside the gaseous envelope of the other one. They're still quite far apart here, but they're spiraling into each other because of the gas. So now from here to here, around 5 million years, they're only 43.8 units apart. This is a helium star now, and then this one collapses into a black hole. So we have 2 huge black holes, 136 solar masses, 130.8 solar masses, and this all happens over about 5.3 million years. They're both black holes, and then 10 billion years later they merge. So this isn't the scale, this timeline. There's a bit of a gap at the end. So this is the mainstream interpretation of what happens, but because the masses are so large, it seems somewhat rare or somewhat odd that we detected such a large event. And this is brought about speculation that maybe these larger solar mass black holes are more frequent than we thought. And maybe, just maybe, these are primordial black holes left over from the Big Bang. And maybe this is one of the sources of dark matter. As you may recall, there has been a long-running discussion about what the dark matter is. And there's always been the WIMPs and the machos, the weakly interacting massive particles and the massive compact halo objects. So black holes would be machos, WIMPs would be like neutrinos or heavy exotic mass particles. And over the years, more and more evidence seems to have gathered or accumulated for WIMPs being the source of the dark matter. Most people think that it's some sort of strange, non-baryonic matter beyond the standard theory of physics that's the source of this based on cosmology. But some people are starting to speculate that maybe if we detect more of these high mass black hole mergers in coming years, this will swing the pendulum back the other way. In fact, there are other observations that support the theory of black holes being the source of the dark matter. And just to think, if these are the source of the dark matter, there might be 10 to 30 billion of these black holes orbiting in a halo around our galaxy alone. But this is just speculation at this point. And I think as we get more data from these laser gravity wave observatories, we're going to find out a lot more on whether this is actually a viable theory or not. Nobody really knows if black holes would have formed in the Big Bang, what formed them, what matter went into them, and how could they be binaries. One would think that they would probably be all on their own and they wouldn't be in a binary pair, whereas the stellar theory gives you a reasonable explanation as to how they came to be. So some interesting stuff going on in the theory, and we'll learn more in coming years for sure. And the final image is one that I thought was a hoax when I first saw it. Is the one on the right, and this was a picture from Hubble of an aurora on Jupiter. And I thought, oh, come on. That's not a real picture, that's been doctored. But, you know, it's got ESA and NASA on it, and it links back to the websites. And so I did a little more digging, and I found that, okay, this is a superposition of two images. The aurora is a far ultraviolet image from a camera that only looks in the far ultraviolet. In fact, what it sees is on the left. And this is superimposed onto a visible image by the Hubble Space Telescope. And so what's happened is that Jupiter has huge magnetic field, a lot of radiation. This aurora is continuously going on Jupiter. And Hubble now has an instrument that's been looking at it over time. And I'm going to play an animation of this over several rotations, hopefully. So you can see Jupiter's aurora, which is really cool. So this is actually what it would look like if you could see into the far ultraviolet and visible at the same time. So it's just a really cool image. And I'll leave you with that. Thank you.
The rotation of the aurora, is it in time with the rotation of the planet?
I believe so. It would be locked to the magnetic field. I mean, to say, you know, I think that's probably rotating with Jupiter. Yeah.
What's the approximate diameter of that oval? Do you know?
Yes, probably a few Earths, actually.
Well, the red spot is what, 2, 3 Earths? So
Yeah, the red spot's almost 3 Earth diameters, so you can measure.
So about, you know, 4 or 5 Earth diameters. Pretty cool.
big.
All right. Thanks.
All right, thank you, Al. Of course, Jupiter also in the news because of the Juno spacecraft that's just rendezvoused with Jupiter. I don't know if someone can shout out. Does anyone have any updates on Juno and on how it's going?
50 days till it comes back to do observation.
Okay, all right. So it's still a while yet. All right. So now we'll move on to our tech master, Eric Kujala, who's got a presentation on the transit of Mercury, but this time from the vantage of SmartScope.
Hey folks. First I'd like to extend my condolences to Linda and the family. Watching Rolf up there a few minutes ago made me feel like he was with us again. I've had the privilege of recording many of Rolf's presentations over the years, and I would invite you to revisit those. They're all available on our archives on YouTube. And I find that every time I look at one of his presentations, I'm learning something new again. So I would invite you to do that. Someone said that when you pass on, you simply cease. Some people say you go to heaven, and some people say that you go to the stars. And I was thinking, if he's up there in the stars, he definitely knows where everything is. And he's probably showing everyone else up there what's going on too. All right, on to SmartScope. During the Mercury transit, most people were either on Parliament Hill or watching it through their telescope at home. It was a huge event, and I had the privilege of joining two other fellows, Jim Maxwell and Wolfram, at SmartScope, which is located at Shirley's Bay in the west end of Ottawa. If we could go to the next slide, please. So this is SmartScope. It's on a government site, so it's not accessible to the public, not very easily. And that's actually a good thing, because SmartScope is designed to be used online. At least that's where we're going with it. It's a fine instrument, but it's online capability that's going to make a big difference for us in the future, where members can, from their own home, can log in and use this wonderful telescope. We were on site because we wanted to make sure that everything worked, and we webcast the event that day, and we had quite a few people watch on the internet. People are watching on the same channel we're on right now. So we started at 5:30 in the morning. If we could go to the next slide, please. That's it right there. I don't know all the technical details of this instrument. I could tell that the instrument itself has a lot of capability, something that hasn't been tapped into yet, especially with the sensor we were using. If we could go to the next image, please. So that's our setup inside. So on the right side, we see the computer that controls SmartScope itself. The computer in the middle is a link between my computer and that computer so that we could webcast the images. And you'll see on the middle computer, there's an image of Mercury during the transit. If we go to the next image, please. While we were webcasting, we would take breaks and we would go out and actually look at the transit through a smaller telescope, which Jim set up. And I really enjoyed seeing Mercury optically. You know, looking at something electronically is fine, but you always want to look at an object optically. There's something about that just doesn't translate electronically. Next image, please. So Wolfram was operating the SmartScope. Next image, please. And these are some images I captured during the transit. So this is during the ingress period, just after ingress. We actually found it was hard to find where Mercury was going to enter in the transit, which none of us expected. We thought we'd be able to find it right away. So it took a little while, and by the time we got to it, it already had ingressed a few degrees. Next image. We also put the sensor, which is a NextImage 5 sensor, not a very expensive sensor. It's what we have to work with right now. We put it on the guide scope so we could get a full image of the sun during the transit. The SmartScope is it really focuses in pretty far in there. It's only I don't know how many arc seconds it actually captures, but it's a very small window of the sky, which is to your advantage when you want to look at something very far away. But because the sun is so close, we could only see the planet and a part of the sun with the SmartScope. So we use the guide scope to take these images. So to the left side, we see Mercury right here. And this is a large sunspot that most people are watching at the same time. I thought viewing the sun itself was exciting enough, not just looking at this planet going across. Next image, please. Through the day, SmartScope changed. Obviously, it was tracking the object, and I was impressed at how smoothly it could do that. Next image. And here's another shot of Mercury through SmartScope. There's the larger sunspot that we were viewing that day, some smaller ones. This is the first time I've actually seen Mercury as a spherical object. When we look at it in the sky, around dawn, we only see a blip, at best. But what the sun was doing that I had never seen before is actually highlighting that it is a spherical object. Next item, please. And there's about as good a close-up as we got. There's obviously a lot of atmospheric activity that blurs things out. We saw a lot of that during the transit, a lot of clouds going through. So we never got a really sharp image of Mercury during the transit. Next item. And during the egress. This what really impressed me because they had predicted the egress to the minute. almost to the second. And, I'm watching this thing going by and I'm saying, no, it's not going to make it there by that time. And sure enough, it did. Almost down to the second. It's actually hard to tell when the egress is completed because as it moves out, you lose definition of where it is. Next item. And there's the three of us enjoying a beautiful day. We were thankful. It was a sunny day, and we got. And this was my first experience with SmartScope. I'm really excited about this device. It will offer us a lot of opportunities in the future. There's no limit to the number of things we can look at in the sky with this thing. Next item. And okay, so we were back to the one. So that's my experience, and I wanted to share with you, and I encourage all of you to keep track of what's going on with SmartScope and to take an interest in it because it's something we really need to use. Thank you very much.
Thank you, Eric. Just before we go on to the break, just one sort of preliminary announcement. Up at the front near the laptop computer, there are envelopes available if you would like to make a memorial donation to the Royal Astronomical Society of Canada in memory of Rolf Meier, and and then there's the information on the front of the envelopes. For those of you who are tuning in online, there may be a feature to do it on the RASC website, but I'm not 100% certain about that. That may require communication with another center member. Sorry?
It is working.
Oh, it is working? Okay, good. Is it on the Ottawa or is it on the national site? Okay, so on the national site, there's a donation feature that you can use to donate money to the RASC in memory of Rolf Meier. So with that, we'll take a break of about 10 minutes, and we'll reconvene, and we'll have the second part of the meeting. Raffle tickets will be available up at the front. All right, so see you in 10 minutes. So just before we continue on with the program, I'm told that our president, Gordon, the illustrious. Do we have a superlative for you yet? Gordon. Anyway, Gordon, our benevolent leader, has an announcement. So take it away, Gordon.
Yeah, just one thing I wanted to add to what we've already said tonight about Rolf. Council is in the process of creating the Rolf Meier Award for Planetary Observing, which will be handed to or awarded to people who excel in planetary observing. So, thank you.
Thank you, Gordon, for that announcement. So I'm sure the Meier family would be very happy with that tribute, that lasting tribute to Rolf. So if we go on, our next. Oh, sorry. This is something that we sometimes show. These are the benefits of membership if you choose to become a member. All right. The next talk will be by Konstantin Popov, and it's structure of focused light beam and telescope resolution. So this is a very science-focused one for you science geeks out there. Take it away, Konstantin.
You could have the house lights, please.
Well, there won't be much science actually in this talk. I tried to keep it actually very short. I only have several slides, and also tried to keep the technical details at the very minimum possible. So my name is Konstantin Popov. I'm a pretty young member of this society. I've been with you just for a couple years. This is my first talk here. So just to give some motivation, I used to work at the University of Ottawa, where part of my job was doing some calculations for laser propagation in optical media. And those very algorithms could be very easily applied to the visualization of light inside the telescope. Can we keep it down? Because of the feedback. Okay, yeah. So I think the results are nice, so I just thought it's a good idea to share them with you. So this is what I consider to be focusing optics.
Sir, if you could come closer to the microphone, please.
This one?
Yeah, just stand
Okay.
closer to the microphone. The other one. There we
This
go.
one? Okay. Okay, so we'll have all kinds of different telescopes of different designs, and many of designs have particular features to eliminate or reduce major aberrations. I don't really want to concentrate on a specific design. On the other hand, we need something to model, and this something better be something simple and natural aberration free. So paraboloidal mirror, as shown here, actually is a good candidate because it has those properties, especially if we are only concerned with the on-axis performance. So what we have here is light from distant star, normally incident into this mirror, and when they reach the surface, when light reaches the surface, it gets reflected. So the light rays converge towards the focus. Now, if those were real rays, they would converge to a point of zero radius. We all know that this is not what's happening in practice. Due to the wave nature of light, the radius is limited by the wavelength, and in practice also depends on the geometrical properties of this paraboloid. I will talk a bit later about it. So before showing you what the light structure is, let's just quickly discuss what is light. There's more than one major theory describing light in science. It turns out that for the problems of optical beams propagations, the classical electromagnetic theory works pretty well. And from the point of view of the theory, light is an electromagnetic wave, meaning it consists of electric and magnetic components. Each of them is a vector itself, which means that it has magnitude and a direction. We'll know, for example, that magnetic field of Earth has direction. We can measure it with a compass. Same with the electric field. So these are two vectorial components that are part of light. In 3D space, each vector is described by three components of this vector. So altogether, light can be described by 6 quantities. The simplest form of this electromagnetic wave is animated here. It's a so-called plane wave. Plane wave propagates along a straight line, and it has this property of translational symmetry, meaning that if you shift in the perpendicular direction, you will not see any change in amplitude. And therefore, it's called plane. Also, if the polarization of this wave is linear, only one component of the electric field will be present, only one component of magnetic field. They will be perpendicular to each other and perpendicular to the direction of propagation. So this is simplest kind of light. And luckily, light from distant stars can with very good accuracy be represented as a combination of this plane wave. So if we know how to focus plane wave, we know pretty much how to focus starlight. I'm sorry for not having animation for the focused light. I realized too late that it would be spectacular. But this is what I have. This is electromagnetic field components in the focal plane. So when you focus it, so this is image, but not image the way that we normally see in the eyepiece, but rather individual components of the electromagnetic field. So this row here shows electric components, and this is magnetic components. So in this figure, this is component along the propagation. This is one perpendicular component. This is another perpendicular component. And this one, by the way, coincides with the polarization of original plane wave incident onto the mirror. In my opinion, these are beautiful pictures. And this is recognizable shape of central spot with diffraction rings around it. So this is what we normally see in the eyepiece. And this is a dominant component. If you try to visualize the focused beam, you will realize that it is inevitable that since there is an angle between optical axis and the converging light, it is inevitable that there should be a longitudinal component as well, which is shown here. And it turns out there is another component present there as well. Now, how is it connected to what we see in the eyepiece? In the eyepiece, what we measure, what our eye measures, is intensity of the light. And roughly speaking, it's each of these components. If we square it and sum all these components together, then time average, this is what we see by our eyes. And this is, well, I've made a classical mistake assuming that dynamic range of projector will be the same as my monitor. But believe me, there should be a diffraction ring here. Yes. This is pretty much the same visualization, only in a different plane. So this is a focal plane, and focused light, the light will focus from, the mirror would be here, it would be focused in this way, in this direction. So we can see that in the focus, the most of energy is concentrated in the central spot, and the least goes to the diffraction rings. However, if we shift from the focus, more and more light will go into the diffraction rings. And actually, there are holes. So here it would look in the eyepiece as a donut shape, followed by, again, some central spot here, not very well visible, but it's there. I would also like to discuss one more thing. So let's look closer in the focal plane and plot the intensity of the beam as a function of coordinate in the transverse direction. So what we will see is the central spot that goes to the minimum, then diffraction ring, minimum, another diffraction ring, and so on. Now I would like to pose a question. So if we had two shapes like this, close together, like here in the inset, how close should they be? Can they be so that we still can definitely say that there are two shapes there rather than one? So this is a problem of resolution of the optics. So different people have different eyes. So for one person it will look like two stars. The other person will say, oh no, I only see one. So to quantify things, there are different criteria, and there is the most commonly used is so-called Rayleigh criterion. That states that the resolution of the image is determined by the distance between the peak and the first minimum here. And this is the approximate formula to calculate it. So there is the focal length of the mirror, wavelength of the light, and the mirror diameter. Now when we look at the eyepiece, what's important for us is the angular resolution. So the angular resolution is given by formula here. The angular separation between this minimum and maximum is proportional to the wavelength, meaning that for the two blue stars, will actually look more like two sources. So the resolution for blue stars is higher, the separation is smaller. And the red stars, if we're trying to separate two close red stars, it will be more difficult to do. Separation is inversely proportional to the aperture of the telescope, which is a common sense for all of us. Last thing I would like to discuss is what about abstracted optics? So in the same way as we were able to show details of the field for mirror, we can just block part of it and we can model the same way the abstracted optics. And sometimes we can hear that, well, refractor is better because it's not abstractive. Well, how much truth is in those statements? The answer is, well, it depends on your goal. So if we look at this picture here that I plotted, the blue line here is intensity distribution for the unabstracted optics, and this purple is distribution for the abstracted, 40% abstracted by diameter, which is 16% by area, which is not that uncommon. Usually it's a figure of the order of 33% or so. So what we see, first, the peak intensity is considerably disproportionately smaller for abstracted optics. It's smaller by, well, at least a quarter, and definitely not 16%, which means that point sources, all things being equal, in the refractor will look brighter. The reason for that is, whereas the central peak here contains more than 85% for refractor, for reflector, for abstracted optics, the figure is closer to just 60%, and the rest will go into the diffraction rings. And one other consequence is, well, these rings themselves will be much more visible, and if we have a low contrast feature in the image, they will smear them out. So the contrast by the abstracted optics will also be considerably worse. On the other hand, if we look closer here, we will see that actually resolution of the abstracted objective is better by some 10–15%, and this is, by the way, a well-known feature, and this is one of the way, for example, in linear microscopy, to boost resolution at the expense of the contrast. So, depending on your goals, if the resolution is something that you care most about, well, you might want to choose reflector and be happy with it. If contrast is more important for you, then, well, maybe the refractor is a better option. That's it for me. Thank you for your attention.
Thank you very much, Konstantin. And now we move to the always exciting talks by Simon Hanmer. So take it away, Simon.
Well, I'd just like to say before I start that it really is an honor for me to actually be on this program at this meeting in honor of Rolf Meier. Okay, when NASA's New Horizons probe performed its flyby of the Pluto-Charon system exactly 12 months ago, I gave a presentation to this meeting where I discussed the already exciting, not to say surprising, preliminary images in a talk that I subtitled Geological Speculations Based on Minimal Data. Most of those initial images were relatively low resolution, something in the order of kilometers per pixel. Next slide, please. Now, this is how we saw Pluto in 2015, and the big excitement at the time was that the surface was clearly recently geologically active. A large heart-shaped area, that's this, and then there's another lobe over there, of smooth, therefore relatively young, predominantly nitrogen ice, no older than about 10 million years old, overlies older water ice with abundant impact craters. Now, this requires that the insides of Pluto are currently hot enough to at least partially melt ice in the frigid conditions of the outer solar system. And we're talking here something of the order of 30 to 50 degrees Kelvin, not Celsius. Which raises the still unanswered question, what is generating the internal heat in a dwarf planet that was supposed to be old, cold, and dead? Next slide, please. Since that talk, the New Horizons probe has successfully transmitted its high-resolution data, that's to say of the order of 100 meters to a kilometer per pixel, giving us a very clear picture of what the imaged parts of Pluto and its moon Charon would have looked like to a well-equipped astronomer on board the New Horizons spacecraft, presumably with a good pair of binoculars and a small scope of some decent quality. Next slide, please. Now, NASA has now released a wealth of selected and processed data into the public domain, principally in the form of superlative, and I cannot emphasize this enough, superlative images, such as this detailed illustration of the young, low-lying, impact-free nitrogen ice field here, which is known as Sputnik Planum, and I'll be referring to that name a number of times, and the older, rugged water ice highlands. You can see those here, as well as Pluto's beautifully stratified atmosphere, which I don't need to point to with the laser pointer at all. Next slide, please. Now, associated university-based planetary scientists have now started to publish tentative interpretations of what it all means. Most importantly, there's been a set of 6 papers which was published earlier this year in the highly reputable Science magazine, and this is really key, they're available to the general public online. Now, this image here that you can see serves 2 purposes tonight. Firstly, to show you a few key locations and their names. So, for example, here is Sputnik Planum that I'll be referring to. This part of the Tombau Regio simply means region. And you might notice these maculae over here, that's the plural of macula, which simply means spots. I did actually talk about them last year. I'm not going to have time to talk about them this time, but by all means, ask me questions. And secondly, to illustrate the difference in photographic resolution between the area that was actually imaged during closest approach, that's this area here, and the rest of Pluto that was imaged from much greater distances, which is why it's so fuzzy. Next one, please. Now, much of the scientific work that's now in the public domain continues to focus, did I do that? Continues to focus on the source of internal heat within Pluto. However, so much of this effort is highly speculative. The bottom line is that nobody has any hard and fast data to work with. They weren't expecting any heat, so they didn't detect it. So tonight I'm going to focus on the features we can observe directly thanks to this new high-resolution imagery, features that we can attempt to interpret for ourselves and compare with what the professionals are saying about them. Now, NASA and its associated scientists have done a great job of mapping and classifying different terrains, nicely illustrated in this image. Each one of these color patches here is a different terrain. However, while they're arm-waving about Pluto's internal heat, they remain somewhat cagey when it comes to interpreting the visible surface features. And this is a case in point, as the authors of this article clearly point out. This article here, by the way, which is one of the published ones. This is a terrain locator map. This is not a geological map. And that means it's an inventory of colors, shapes, and textures, as opposed to an interpretation of processes and their significance or meaning. Next one, please. Now, as a prime example of what I mean, let's look at Sputnik Planum, which is this here. In other words, this here. A year ago, we already knew that Sputnik Planum was made of nitrogen ice divided up into large polygons, about 100 kilometers long and several tens of kilometers wide. And since then, NASA has released a number of highly detailed images of the Sputnik Planum nitrogen ice field, with emphasis on its margins and its internal polygons. And planetary scientists have been deriving numerical, that's to say computer, models to explain it. So let's take a look. Next one, please. Good. Now here's a nicely detailed image of part of the boundary between the smooth Sputnik Planum, that's here over here, made of mechanically weak, and that's important, mechanically weak nitrogen ice, and the rugged highlands here, made of mechanically stronger water ice. That's why there are highlands. The ice is strong enough to hold them up. It's pretty clear that the nitrogen ice gets progressively thinner as you approach the highlands, and it sits on top of them. So we can talk about a nitrogen ice cover over the top of a water ice basement. You can make out headlands, such as this one up here. There's actually one down there too. And bays, such as here, here, and even here. At the edge of what NASA has labeled hummocky marginal plains. I don't know about hummocky, I would call it blocky, but we'll come back to that in just a minute. Now, these promontories will be an important observation later in the talk. So take a good look at this one here in particular, and actually have a good look at that one too, and bear them in mind. I will remind you of them. Next one, please. Now, this NASA image actually dates from July 2015, from last year, and it was already clear that the nitrogen ice has flowed from the interior of the Sputnik Planum towards the highlands. And this is especially clear up here. You can actually see the flow marks in that ice there. Now you can see the polygonal shapes within the nitrogen ice. That's these things here. Each one of these is a polygon. And they're especially well highlighted towards the edges of the young ice field. Notice how dark grey the ice appears to be along its margins. It appears to be altered as it's getting thinner. And anyone that's worked with fixed-wing aircraft landing on still frozen lakes in northern Canada during the spring will recognize this. The ice is degraded. It's weakened. It's less coherent than where it's thicker in the interior. This also might explain why the boundaries of the polygons are so easy to see in the marginal areas. It's intriguing that while planetary scientists have noted the color change at the margins of the nitrogen ice field, they've not provided any interpretations for it yet. Now, flow of a sheet of weak nitrogen ice over strong water ice basement could be explained by either of two processes: glacier flow or cryovolcanic flow. Cryovolcanic simply means volcanism, but instead of hot magma, it's volcanism with ice as the medium. Next one, please. And last year, NASA and its associated planetary scientists decided upon a glacial model that they're still promoting, and this is part of the evidence. They suggest that these linear, that's a blow-up of this linear area here, and lobate features, such as this one here, there are other linear features here and here and here. They suggest that these indicate that the nitrogen ice accumulated in the highlands, which are over here, and then flowed down as mountain glaciers onto Sputnik Planum, which is here. But there are two problems with this, at least two problems with this. First, there are no ice fields up in the highlands. In other words, there are no relic sources for these mountain glaciers. And secondly, given Pluto's thin atmosphere, it's really not obvious how to build the purported nitrogen ice mountain glaciers in the first place. Remember, nitrogen ice on Pluto rains out of the atmosphere as frost, not as thick accumulations of snow, which are required to build glaciers. Now, last year, I found NASA's interpretation to be already highly speculative, and a cryovolcanic process sourcing mobile ice from within the dwarf planet made most sense to me. Well, these new high-resolution images, it turns out that with these, you can actually have your cake and eat it too. We could all be right, at least in principle. And I'll get to that in just a minute, but first, how about some more observations? Next slide, please. Now, in this detailed image of the margins of Sputnik Planum, you can see the pristine water ice highlands basement on the left. That's here, that's the pristine stuff. And you can see the white polygons of nitrogen ice over here on the right. And running down the middle of the image, we see a swath, that's this stuff here, of chaotically, randomly blocky basement with blocks up to tens of kilometers in diameter. And it is bordered to its right by degraded nitrogen ice, thin. We know that that nitrogen ice is thin because we can see peninsular islands such as this one here. That island hasn't quite been cut off from the mainland. And it's surrounded by nitrogen ice. So once again, we see evidence for the fact that the nitrogen ice is a cover sequence over the water ice basement. Next one, please. And this is the same image, essentially, but with a digital elevation model, which is what this is down here. There again is the nitrogen ice, the water ice basement. Here's the blocky area here. And you can see that with the reddish-pink colors, these blocks here are actually higher than either the water ice basement in the lower part of the image or the nitrogen ice of Sputnik Planum to the upper part. Next one, please. So how do we explain these observations? Planetary scientists suggest that the very young, that's to say less than 10 million year old ice of Sputnik Planum, may fill a very old, by that I mean 3.8 billion years or thereabouts, impact basin, similar in age and in nature to those we observe on the moon. So this is Sputnik Planum, and when I mention the western margin, it'll be here, and the eastern margin will be over there, actually all the way down there. However, they then get equivocal and couch things in the conditional. They cautiously intimate that the blocky highland terrain we can see here. You can see the blocky highland terrain very nicely illustrated here, and perhaps up there too, but absent over there. They suggest that it's actually related to an impact basin, but impact basins, as you know, are multi-ringed features resulting from initial cavity collapse. And I know of none in the solar system that formed localized impact breccias with blocks up to 10 or 20 kilometers across and 5 kilometers high, as these things are here in this image. Now, a year ago, I speculated that the blocky margins of the water ice highlands might represent chaotic, weird terrain. That is the technical term, resulting from the global refraction and focusing of forces from a massive impact on Pluto's unseen, therefore hidden side, so one can say what you want about it. The type example of weird terrain is on Mercury, and it forms dead opposite to the Caloris impact basin. And weird terrain does indeed comprise blocks of about that kind of size and height. Now, in addition, weird terrain itself is usually irregular in overall shape, as opposed to circular impact basins, and that possibly provides an explanation for the otherwise puzzling absence of that blocky highland terrain along the eastern edge of Sputnik Planum. Now, the planetary scientists then go on to suggest that the nitrogen ice was originally thicker than today, and therefore extended further onto the blocky highlands. Furthermore, they speculate that the nitrogen ice may have played an ill-defined role in modifying that blocky highland terrain through a combination of undercutting, flotation. Turns out that under these conditions on Pluto, water ice floats in nitrogen ice, provided that both are solid, and rotation of those blocks. They then go on to suggest, and I've got to point out that these suggestions and speculations are one-liners in these scientifically reviewed papers. They then go on to suggest that at some unspecified later time, the nitrogen ice retreated, possibly by sublimation. Sublimation which also led to degradation of that nitrogen ice, exposing the water ice basement and leaving behind relic patches of nitrogen ice. The blocky water ice highlands were then modified, according to this story, by glacial erosion as the nitrogen ice flowed down from those relic patches down to the edges of Sputnik Planum. Next one, please. So what I take from all this is that impact-related weakness in the water ice basement, possibly in a weird terrain setting, may have localized much later eruption of nitrogen ice from Pluto's interior. This is exactly what happens on the moon, the relationship between impact basins and their timing and the timing of the magmas that actually fill them after. There can be up to 500 million to 1 billion years time difference. Nitrogen retreat by subsequent sublimation exposed the marginal water ice highlands that were etched by erosion when the relic nitrogen ice flowed as mountain glaciers onto Sputnik Planum. In other words, Formation by cryovolcanism would have been the main Sputnik Planum event, followed by minor modification by glacial flow, and hence you can have your cake and eat it. Next one, please. So let's now turn our attention to the polygons of nitrogen ice of Sputnik Planum. Planetary scientists have been looking at the polygons using numerical computer modeling as their primary tool. And in doing so, they propose that the polygons, which you can see up here in this image here, which is a summary image essentially, may be the tops of large, recent convection cells in the nitrogen ice that was therefore warm enough to rise in the polygon interiors, flow outward at the surface, and cool enough to then sink back into the ice along surprisingly narrow margins. But here's the problem. You can fine-tune, or more directly, over-constrain computer models to produce the results you want. Thermal convection is highly dependent on heat flow from below, and we don't know what the heat flow of Pluto is. So you can tweak that as you wish. In addition, the convection geometry, the polygon size and shape, is dependent on the thickness of the convecting material. We don't know how thick the nitrogen ice is. So you can play with that to your heart's desire in your computer models. So planetary scientists have indeed been making major assumptions in order to run their computer models. Now that's fair enough as a test of feasibility, but it is not a test of causality. So bearing these caveats in mind, let's take a closer look at what's been going on in these polygons. Next one, please. Now, the convection model, something I got a lot of personal hands-on experience with in the geological context, as calculated by planetary scientists, predicts that the upwelling interiors of the nitrogen ice polygons in Sputnik Planum stand about 10 meters higher than their supposedly downwelling margins. The standard model, which is well established, for convection cells predicts that the downwelling areas should form broad troughs. Think the coronae structures on Venus. But in most of the Sputnik Planum pictures, the polygon margins are not broad troughs at all. They are unusually narrow and they're parallel-sided. However, take a closer look at this image here in particular. The polygon interiors are pervasively covered by small 1 to 2 kilometer diameter pits. That's these little things here. They're everywhere. Very likely the result of sublimation, though I have no explanation for why the sublimation would form such a uniform, localized texture. Nor does anybody else, by the way, and in fact, the observation is generally ignored. Now look at the pits. As you can see the illumination of their walls, you can see that they're illuminated on their southern side, assuming that's north, which means that the sun is shining from the top of the image. Now, highlights and shadows on highlights and shadows along the demonstrate that the purported downwelling margins of these polygons are ridges, not troughs, though this is not the norm for much of Sputnik Planum. Now, planetary scientists have not ignored this, but they describe median ridges, in other words, ridges in the middle of troughs, similar to the tri-band linear structures I told you about on icy moons in the outer solar system a couple of years ago. But that clearly is not the case here. These are simple ridges. Now look at the pattern of ridges at the polygon margins. That's what these things are here. And you notice that in places, they've lost their relief. You can still see the trace of where they went, but they no longer have any relief. And they've been subsequently overprinted by these sublimation pits. Hence we have a time sequence, purported convection cells first and sublimation second. By the way, the same observations apply to the more normal marginal troughs throughout Sputnik Planum, but those marginal troughs are as narrow as these ridges. So how did the ridges lose their relief? If they'd collapsed under their own weight by what's called viscous relaxation, then they should have spread laterally, becoming wider. That's not what we observe. So what's going on here? Well, in reality, I don't know, but hell, if they can speculate, so can I. What if the ridges were dense enough to sink vertically back into the surrounding ice? There's ways of doing it. Finally, notice this small black pip here in the image. Planetary scientists suggest that it's a block of buoyant water ice detached from the margins of Sputnik Planum and floating like an iceberg in the denser nitrogen ice. Possibly so, but note its location. It's very specific. It sits precisely at the intersection, or triple point as it's called technically, between three polygonal convection cells. For the structural geologist that I am, that sets off alarm bells. Next one, please. Oh, let's go to the next one, just in case. There we go. I put one in too many. Alarm bells that were supported by this image of two icebergs, purported icebergs, both of them sitting at that precise triple point position. These alarm bells don't seem to have actually rung at NASA's headquarters. Now, I'll come back to this point in a minute, but let's first look at more of these supposed icebergs. Next one, please. Planetary scientists present this image from eastern Sputnik Planum as evidence that the floating bergs of water ice up to 3 kilometers high and more, that's to say proud of the surface of the nitrogen ice, were derived from the adjacent rugged highlands and are carried by the horizontal flow of spreading convection cells in the nitrogen ice to the polygon margins to form these these hill clusters, or these hill chains as they call them. Now, on the basis of this model, knowing that most of any iceberg is submerged, they then calculate the thickness of nitrogen ice of Sputnik Planum to have been around 15 kilometers in order for the icebergs to have floated. Given that this is a little bit steep, even for an impact basin, they then speculate that the load of the nitrogen ice itself would perhaps depress the floor of the initial impact cavity to make up the shortfall in thickness. However, this line of reasoning is a dead end, because as the planetary scientists themselves point out, beyond a few kilometers thickness, nitrogen ice melts and its density drops dramatically, such that water ice could never float in it at those kinds of thicknesses. But all this is pure speculation by NASA and its associates. So now it's our turn to speculate. Well, okay, it's my turn to speculate. What if the ice mountains are not icebergs at all? What if they are islands? Mountain peaks still attached to the underlying water ice basement beneath Sputnik Planum. Notice how to the upper right, up here, there are hill chains of the same orientation as the labeled ones. The labeled ones are here and here, but you've got them up here too. But in the absence of any evidence for polygons. Notice also how all the hill chains are parallel to each other and oriented at a high angle to the nitrogen ice, water ice boundary. The same orientation as those water ice promontories in the previous slides that I asked you to bear in mind. Next slide, please. So let's now stand back and look at the bigger picture to the east side of Sputnik Planum and evaluate the iceberg model for ourselves. This is what the previous slide showed us. This is now the bigger picture. And I make the following key observations. First, we can now see that hill chains are not chains at all. They elongate to equidimensional clusters of water ice. Clusters like this, or equidimensional clusters like this. And they have an identical pitted texture that's seen in the rugged highlands. There's the rugged highlands, and you can see that they are pitted. Exactly the same as this block up here, referred to as Challenger Colles, that's been interpreted by NASA and its associated scientists as a large iceberg cluster that ran aground in shallow nitrogen ice. Though in the same paper, it's also compared with chaos features on Europa. Secondly, over half of the isolated water ice mountains are actually located at triple points. There we go. Where three polygons meet, and none of the water ice, this is key, none of the water ice mountains occur within the polygons. Okay, so now let's try to piece all this together with some wild speculation on my part. What if the nitrogen ice polygons are not the product of convection due to heating at the base of Sputnik Planum at all? What if the polygons are individual extrusion events, the consequence of melting within Pluto, the rising of cryovolcanic magma, in other words, ice, and its emplacement into a growing Sputnik Planum ice field as a sequence of multiple flattened bubbles? Think of the pancake volcanoes on Venus, for example, or think of Io, where the volcanoes on Io are not mountains, and the mountains on Io are not volcanoes. What if the horizontal surface flow associated with the flattening of multiple synchronous rising bubbles of cryovolcanic nitrogen ice was pinned by the drowned water ice outliers or island clusters? In that case, it would be the polygon margins that were mobile and the water ice islands that were static, rather than the other way round in NASA and Associates' interpretation. Why would the triple points in the polygon boundary network get preferentially pinned by isolated water islands? I'm not sure. But this is exactly what you see in mineral aggregates, and it's exactly what you see in foam bubbles, where the driving force is the reduction of surface energy in the presence of impurities. Could this operate at this larger scale? I really don't know. Nitrogen ice is pretty weird stuff. If my wild speculations here tonight have any validity, they imply that the margins of the nitrogen ice polygons are not the sites of downwelling convection. They are simple interfaces between different directions of horizontal ice flow. They imply that we're not looking at a convection cell model driven by heat from below at all. Instead, we're looking at cryovolcanism driven by the heat of low viscosity, very runny magma, ice, erupting onto Pluto's surface. In short, the polygons can be seen as individual volcanoes and associated lava flows of very runny ice magma. Why then are there no classical volcanic edifices? Again, I take you back to Io, where the lavas are extraordinarily runny and where, as I said, the volcanoes do not form edifices at all, they do not form mountains, and the mountains on Io are not volcanic. They're the results of faulting and rotation of blocks. Finally, according to this model, the one I'm presenting to you, that nitrogen ice of Sputnik Planum could be no thicker than 2 to 3 kilometers, assuming that it's solid throughout. But I hear you say, next slide please, what about the volcanic edifices Wright Mons and Picard Mons? This is Wright Mons up here, and this is a second picture. This is Picard Mons. They even look like volcanoes. They actually have summit craters on them too, as well as being mountains. Quite correct. But they are made of mechanically strong water ice. And they are the only 2 volcanic edifice candidates so far identified. And even the NASA scientists still call them candidates. They don't say they are proven volcanoes. Next slide, please. So before I draw this talk to a close, I've mentioned sublimation numerous times this evening. So what's the visual evidence that sublimation has been, and likely still is, a widespread process on Pluto? Here we see 1 to 2 kilometer pits are pervasively developed in ice. And in several patches, the pits form curvilinear pit chains that coalesce to form curvilinear grooves. You can see it quite nicely here. And you can see it here. See how it curves through like this and then curves out the other way. As a structural geologist, I immediately see 2 belts trending left to right with the curves, the grooves curving progressively across them. Can you hit the forward button again, please? There we go. Now, here's a very famous rock from Scotland. Note the scale. That is indeed a penny. It shows similar curvilinear features developed across. There's the feature here. Comes through like this, comes through and out the other side like this, just like this does. So it develops curvilinear features across a smeared out band in otherwise undeformed rock. This is undeformed, this is undeformed, this is undeformed, and this is undeformed. The shear zone formed when the rock on either side slid sideways and squished the stuff in the middle. By the way, I spent almost all of my geological career working on shear zones. The sense of curvature of the newly developed fabric in the rock tells me that the upper part of the rock slid to the left relative to the lower part of that slide there. It may be much smaller than the example from Pluto, but I suggest the two formed in the same way. The ice was sheared by differential flow within the ice itself, creating a fabric made of planes of weakness that localized more intense sublimation, initially in pit chains that then coalesced to form grooves along the shear zone fabric. If the shear zone itself, next slide please, if the shear zone itself, the smeared out stuff, then gets subsequently deformed by further ice flow, then the belt of pit chains and grooves ends up curvilinear, as you can see up here. See how it's curvilinear? I would suggest that that is actually a belt which has then been subsequently further deformed. Next slide, please. Now, in this example, the aligned grooves are now pervasive and they're quite deep. Notice what we see on the floors of the grooves. This is in color. And you can actually see there's a reddish hue here. And if the resolution is good enough, you'll see that that is a deposit of tholin, a complex hydrocarbon that forms a residue that when ice that contains it sublimates and leaves the tholin behind. And if the resolution is good enough, you'll see that the reddish hue is actually on the floors of these grooves and not on the ridges. And that would then be visual evidence of sublimation. If the tholin simply precipitated out of the atmosphere, they should be on the ridges as well as in the floors. I find it intriguing that NASA and its associated planetary scientists only refer to this very obliquely, though they are in favor of sublimation. Next slide, please. So this is my final slide. However, sublimation would not appear to account for these large pits formed in blocky water ice terrain. That's these things here, 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 and here. Given that these over here are about 2 kilometers across, these are obviously an order of magnitude larger. Apart from this size, they also have clear striations. You can see them here, pointing downslope, down towards the floors of the pits. And you can see them down here very well. I think you can even, no, that's not striations there. And those are clear signs of a component of collapse in forming those holes. Well, that's all we have time for tonight. There's more to discuss about Pluto, a lot more, but that's for another day. My original presentation had something like 60 slides in. I had to get out Occam's razor for this one. Meanwhile, my take-home message tonight is that nothing is yet cut and dried on Pluto with the current state of knowledge, but it really is fun to speculate. Thanks for listening.
Don't go too far yet. Thank you, Simon. Don't go too far yet. We're now going to go. That concludes the main talks. We will now proceed to the observations. So, observations there are by Simon Hanmer, Andrew Brown, and Eric LeMay. So if you could all come down and wait in line, except of course Simon, who's already here. And I would ask our observers to keep their presentations or their reports of their observations as brief as possible. Simon, take it.
Well, you're not used to seeing me in this section, but actually I am a very keen observer, imager, and I've recently gotten into solar time-lapse imaging. And 2 weekends ago, I got really lucky. I use a Coronado 90 H-alpha telescope with a Manicam SSI monochrome camera. If we could have the first image. Oh no, not this one, Chris. It's the other one I want to run. If we can run this one first. You don't actually need me to do much talking on this because it's going to become very self-evident. This is 4 hours of imaging at one image, 1 frame per minute, which is reduced down to about 1 minute. It's just starting. Here it goes. Look at the detail in that flare. And you can see this mini flare came out when this appeared to collapse. I don't know if it really did collapse back down into the sun. I don't know physically how that could possibly happen. How do you reverse polarity on a magnetic field? But there are pockets of light which appear to return back to the sun. I don't know, maybe somebody has an idea. The white here is the clouds were coming in, which is why I had to cut it short. Let's cut this one off now, because you don't want me hanging around here too long. Let's go to the second one. And this one, I would like us to actually let it run twice. This is the solar disk, and this is a nicely big, large sunspot. And I think you can see this spiral-shaped structure here, which is part of the magnetic field around that sunspot. And you probably just saw a white flash here. Watch this area here for dark spots forming. There it is. And there's another one. Watch how this actually moves around the spiral magnetic field. This I took a year ago. And I would actually like to let this one run again. You'll actually see in the upper part here, you'll see as this dies in activity, you'll see more filaments. These are filaments, by the way. These are the equivalent of prominences that you'd see on the limb, but you're looking down on them. And the reason I'd like you to see it again is this, is that you're looking down and we're thinking about this in 2 dimensions. But if we had been standing over here looking this way, would we have seen, in fact, what I just showed you previously? Is this actually coming not only around like this, but actually coming up this way as well? Such that seen in 2 dimensions from here, we would actually get that same, the spiral coming up like this. And I suggest that's exactly what they are. They're exactly the same feature, the same process, the same mechanism, and they're around about the same scale. Thank you.
Okay, so I got a timer, good. Good evening, not a lot of time, got a lot to go through. It's my first presentation, so I kind of went a bit crazy. Just to see what I'm working with, I have an 8-inch Newtonian mid-range go-to mount. And if you're frugal like me and you like to make stuff, I have a custom field battery, Batinoff mask, solar filters that Tara spoke about. These are the ones that we use together. And also a remote-controlled focuser, 3D printed and laser cut using equipment available at the library. Now the main feature this summer was, of course, Mercury. We have a nice little dot, some granularity and sunspots. I believe I have some filamental structure up here, another sunspot coming around the rim. Now this is a stack of perhaps about 10 frames or so. Good definition and granularity, sunspot. Quite happy with this shot. Another, this is head towards the, leaving the sun. Next. Okay. Now can we play this? Now, there we go. It was rather windy that day, so I'm sorry for jumping around a bit, but this is 3rd to 4th contact. It's about twice the real-time speed, I believe. So while this is playing, I'd just like to mention, I only just got into astrophotography seriously in any way about 6 months ago in January, so my next series of images kind of show my progress in terms of quality, and it's just about done there. Okay. Still going. So taking about a dozen or so frames of those.
Is it real time?
It's about twice real time. I used a software, free software, PIPP, Planetary Image Preprocessing, to select some of the better frames focusing on Mercury itself, and it did its best to try and stabilize it. Okay, now using a handful of frames or so, I believe I caught the teardrop effect, right about there. Now this is one of my first objects, very familiar, Orion Nebula, great bright object, high dynamic range. I managed to get the trapezium and some diffuse dust and gas areas. I have an unmodified T3I, so you don't get the hydrogen alpha, but hydrogen 2 shows up rather well. About 30-second exposure is only about 6 minutes. The Rosette Nebula, same evening, longer total exposure time, more frames. Now in my stubs, you couldn't see it at all, so the process of stacking is really quite significant. The Eagle Nebula, of course, the very famous pillars of creation. This is a couple of months later. I have improved my process using longer exposures. Now the Iris Nebula. I would like to mention that I don't have a guide scope, so all this is unguided. Nice point-like stars, 60-second subs now, 50 minutes of exposure. The dark regions are clouds of gas, and this is a reflection nebula, so the central region is simply illuminated by the star. A Trifid Nebula. Now, I'm rather proud of this. I'm up to 2 minutes of exposure. It's named for its 3-lobe structure, including a reflection nebula, an emission nebula, and dark nebulosity bands. And right nearby, of course, is the Lagoon. Very prominent in hydrogen 2. Also, a reflection nebula here. 2-minute subs, no guiding. This was back, not April, it was earlier. All taken on the same evening. It was early on, my first real attempt at taking galaxies. And not ideal, of course, with the moon, but I did fairly well, I believe.
Is that a single low-power image of all that?
No. But what's interesting I like to show about this image is that everything is to the same scale. So yeah, everybody knows how large the moon is, but people don't often realize that there are things in the sky that are simply too faint to see, but if you could, they would actually be a fairly decent size. Now, the next image I have is a revisit of my M51. Now, this is only about 6 minutes of exposure, 10-second sub, so I was really just beginning. Now, 2 minutes of exposure, quite a difference. Definitely showing some improvement there. Again, it's all unguided. 15 minutes for this shot. I also have another smaller galaxy right down here. And the dynamic range on this projector may not be ideal, but there are 3 very distant faint galaxies poking up right about there. A couple of months ago, there was an opportunity to catch 67P Churyumov-Gerasimenko, the comet, amongst the Leo triplet. I tried my best to get it at the time. This is still early on in my learning process. It would be located right there. Okay. And I had done some reprocessing, and I actually believe I may have a hint of it. So this is where it should be. And I enhance it. There we go. So that could be it. Impressive, eh? Now, of course, this comet is well known because we have sent the Rosetta mission to land a probe upon it and take observations. Pure eye candy. This is the Andromeda Galaxy. 2-minute subs, just taken the day before Canada Day. I would like to make a larger mosaic of this. I have an f5 scope, 1,000 millimeter, so it doesn't quite fit. Good definition in the dust lanes, nice dynamic range. And now this was just taken with a simple GoPro up at Teeples Hill, thank you, Eric. And got a nice little meteor right there as well. That's all, thank you.
Hey everybody. I finally got to processing my pictures from when I went to the Winter Star Party this past February. This is the Horsehead Nebula region. which consists of about 4.5 hours of hydrogen alpha and another, I believe it was 4.5 hours of color data. I took this with my Takahashi FSQ 106 with an 8300 based camera. And what struck me was when you head down to Florida, you're only at 25 degrees latitude, right? So while here in the winter, it's still pretty close to the horizon. It's, a good 25, 30 degrees above the horizon. Down there, it seems like it's almost straight up. It's so much higher up, but because of that, you get a lot less air that you're looking through. So you can get a much crisper image down there. The colors end up being a little bit more accurate than what you can get up here because of atmospheric extinction. Plus, you can be out in the ocean swimming in the middle of the night. So this is an experience I have. While I was taking this image, I'll show you more time-lapse that I did while I was there in coming months. But I actually set up my time-lapse rig out in the ocean at low tide and got my camera running for this image. And then as the tide came in, my time-lapse filmed the whole star party and the moon coming down and setting and everything. But the guys like to poke fun at me. They were sitting there on shore while I was waiting out to get my gear in the middle of the night with my bathing suit and my. They were taking bids on my scope in case I didn't make it back. It was like 2 feet deep water. Anyways, it was a bit of a fun experience. So yeah, next image, please. This is Omega Centauri. Now, this is the object that when you go to the winter star party, you have to see this. To give you an idea how big this thing is, this is the biggest globular cluster in the night sky. That thing is about the size of the full moon in terms of how much sky it takes up. You can see this thing without binoculars. And when you look at this through a scope, it knocks you over. It's absolutely gorgeous. This thing has about I think it's the mass of 5 million suns. And at its center, the average distance between the stars, I think is about 1/10 of a light year. So that's pretty close. They've actually just discovered as well, too, a number of years ago, that at its core, you have a intermediate sized black hole, about 40,000 solar masses. So this is taken with my 106 millimeter refractor. And the thing that I remarked about it really was that it's basically the size of M13 when I use my 11-inch reflector. Another thing I noticed too, if you guys notice in the right-hand corner up there, see if I can point to it right there. There's a little galaxy. I've yet to identify that one.
You point at it again?
Right there.
It's a galaxy far, far away.
Yeah. So anyways, that's what I have for this month. In coming months, I'm going to have more of the time-lapse as I described. Thank you.
All right, we've reached the end of the meeting, more or less. Just a few minor, few quick announcements to make. So the first is again for the first one is about star parties that are held at the Carp Library. Do we have the? Yeah. Okay. And so this is the location. There's Carp right there, and it's in the library, which is next to the Diefen bunker. If you need to get there. No. I think that's the next slide that's coming up. There we go. So we've had 2 successful primary dates in a row, which I'm not sure if that's a record for Ottawa, but it's certainly very good. So these are the dates for the next over the next year. So we've got the next one is July the 29th with a rain date of July 30th. Then you can see the next dates for in the coming months. So that's it. Next July. We have this end of summer star BQ at the Fred Lossing Observatory on Saturday the 10th of September 2016, or 2 weeks later if it's a rain date. So save the date. This is hosted. Gordon, are you hosting this? Is this? No, sorry. Okay. Sorry. Oh, sorry. Martha Farkas is hosting this. And but it's bring your own food, members only. But barbecues are available for grilling, and proceeds going to the FLO, is that correct? Yep, good. Estelle's pick of the month, Phillips Moon Observer's Guide. This is something that I'm sure Brian, have you ever used this book?
Yeah.
Oh, good.
He's even given it as gifts.
Oh, has he? Oh, well. So we've got the moon for this month as the pick of the month. All right, now I'll do my quick weird but true. Normally, my weird but trues are kind of satirical or funny. This one's not really all that funny, just a bit surprising, really. So you'll recognize this as an artist's impression or a drawing, a facsimile of the Milky Way, our home galaxy, obviously. So we've lived in it for our entire history. And, but there's still a lot we don't know about it. Interestingly enough, we know, there's some things that we know very well about our own galaxy, but there are other things that we know better about other galaxies than we know about our own. It's the only galaxy we can't see the entirety of, apart from ones which are, too far away to be observed beyond the observable universe. But we're in it. We can't see it, all of it. So we have to make some guesswork. So every depiction you've ever seen of the Milky Way is an artist's rendering or a picture of another similar galaxy we believe to be similar. I think it's something that we don't really think about until someone smacks you in the face with it. Yeah, all those pictures that show the Milky Way aren't actually the Milky Way because we can't see it from the outside. Until recently, we didn't know how many arms the Milky Way galaxy had. The current study is pretty certain that there are only 4, but we originally thought there were only 2 principal arms. Now they think there are 4. We're not sure how many stars there are. It can be anywhere from 100 to 400 billion. And we're not even sure how big it is. It's between 100 and 180,000 light years across, we believe. But we're pretty sure that it bulges in the middle, 60,000 light years thick, but by us, it's just 3,000 light years wide. Oh, someone got the joke. Thank you. All right, so that's so still a lot we don't know about the Milky Way, despite having spent our entire history in it. If you would like to become a member, I encourage you to. These are the prices for membership. There are a lot of benefits for joining. One of them is you can take out a telescope from the Ted Bean Loan Library. Is there a deposit for that? $10. It is a $10 refundable $10 deposit, isn't it? Yeah. Yeah, $10 for 1 month. So it's a good deal. You also have access to the site of the Fred Lossing Observatory, but not the buildings. The buildings require a separate fee. You get these publications, and these are some of the more these are some of the important members of the club. And I will say that it only happens once very few, I'd say once every decade or two. Art and Anne Fraser are not here today, so unfortunately you can't get your membership cards from them. This, for those who want to who are tuning in, this is the live stream website. Again, very gratefully provided by our tech master, Eric Kujala. And you can always view the older meetings on YouTube. And this is the video archive. Tonight's audience, 98 members. Thank you to all the organizers and speakers and to our host. Once again, meeting held in honor of the memory of Rolf Meier. So thank you very much for coming down or for joining us online, either live stream or through download. Post-meeting meeting at Gracie's. Hope to see you down there, as many of you down there as possible. Our next meeting will be Friday, 7:30 p.m., August 5th, so back to the first Friday of the month in this building. And so that's 4 weeks away. So we'll be back to the normal rotation. Door prizes afterwards. We'll have the draw. One last chance to get your tickets. Thank you very much for coming, and I hope to see you all next month. Thank you.